and welcome to the lecture series on noise control in mechanical systems with me, Professor Sneha Singh from the Indian Institute of Technology, Roorkee. And we have been discussing about sound absorbers, and we have had a discussion on porous fibrous sound absorbers. Today, so this is what we have been discussing about. And how their sound absorption coefficient is measured, what is NRC, which is the noise reduction coefficient for these absorbing materials. But sound absorbers, they can be classified into lot of groups such as the porous fibrous sound absorbers, panel sound absorbers, then perforated and micro perforated panel sound absorbers, and then Helmholtz resonators and metamaterials. So, we will see the next type of sound absorbers, which are the panel sound absorbers in this lecture, and we will just give the introduction, the working principle and the resonant frequency for this absorber, what is the effect of the air gap which plays a very crucial role in the functioning of this absorber, what are the advantages, limitations and the applications of these kind of absorbers. So, let us see, as the word suggests, panel sound absorbers. So, panel is what? In mechanics or in the field of mechanical engineering, typically a panel is anything which is a thin plate of metal or a thin plate of wood. So, basically a thin plate which is not pervious and non-porous, and it is stiff enough that it acts like a rigid body. So, it is not like a rubber band, stretched rubber band which will actually become a membrane, but it is rather like a thin sheet of metal or a thin sheet of wood. So, in the field of the noise control, because before this we studied about porous fibrous absorbers, there they have got a lot of pores, holes and perforations for the sound waves to enter into the material. But after the porous absorber, in the panel we have no holes and pores. Okay, so this is a non-porous and a non-fibrous absorber. So, basically these absorbers are non-porous and non-pervious thin sheets of metal or thin sheets of plywood or any kind of stiff lamina that you can examine. It could be any material like a metal, a plywood, a gypsum board, but it has to be non-porous, non-pervious and thin sheet of stiff lamina. And then when they are configured in a certain way inside a closed indoor space, they behave as an absorber at low frequencies, okay? And they dissipate the sound energy by the means of the vibrations of these panels itself. So, there are two types of these panel sound absorbers. The first is the freely suspended, which is hung from the corners, and then we have the fixed, which is fixed along its perimeter, and within the fixed type we can say that it also has a sealed air cavity, or the cavity could be filled with some other absorbing material. So, let us have a look at them to see what is freely suspended and fixed. So, when you have got a kind of a panel and from its corner you are hanging it, okay, that becomes a freely suspended absorber, and you have seen a lot of false ceilings, and where these panels are just hanging on the top of the ceilings, they are freely suspended panels. And then the fixed panels means sometimes on the walls you have these panels installed or in the roofs as well. So, they are fixed all along its perimeter, they are not hanging freely from the edges. So, again see, this is a fixed panel and this is your panel, right? This is your panel, this part, it is a panel, and then this shows the clamping condition or the mounting condition, which means that all along its perimeter it has some adhesive has been applied or some kind of welding has been done, but through some mechanical means this particular panel here, this thing here, the one that I am sort of coloring with a red, this panel here through some means is being firmly fixed to a rigid wall. Okay. So, what goes on inside this particular panel, in the fixed panel? So, this shows the inside view of this red portion. Okay. This is the red portion here, which is your panel, Okay. This is your panel. What is there inside? You can see that it is made up of a thin plate because it is a panel type absorber. So, you have a thin plate and then you have this thin plate attached to a rigid box, and there is some sealed gas behind it. Some depth d is given, which is called as the air cavity depth. Okay. So, it's as simple as that you can either have a stiff panel hanging from the roof, or you can have a panel attached to a rigid backing. And how do you attach it? You make a box kind of a structure and you attach it to that rigid wall with this structure where you have this panel which is free to vibrate, and it is being backed by a rigid box which contains a confined gas or a sealed gas. Okay. The gas has no means to escape. So, whenever the panels vibrate, the gas, they would try to oppose the vibrations by the means of their own bulk modulus. So, this is one where you just have a gas being sealed behind the panel or the plate. The other configuration would be that within this rigid box you can also have some lining of absorber material, because typically what we find is that the panel absorbers, they absorb at low frequencies, but their high frequency absorption is not as great. So, why do not we combine the advantages of porous fibrous absorbers which perform really well over a broad range of high frequencies, and we combine it with a panel. So, the general practice now for the noise control engineers has become that when you make these fixed panels, you have a panel and then a rigid box and a sealed air, but with some absorber lining as well to further enhance the absorption characteristics. Sometimes the entire cavity itself is filled with the absorber, and sometimes what happens, the cavity, they are partitioned. So, multiple different absorbers of different volumes are kept inside within this sealed cavity. So, this shows some of the examples. Here you can see an office space or open office cubicle, and these hanging panels, this is the wire. I do not know if it is visible or not, but these wires are there and they are hanging along its corners through these wires and they are held there. So, why are they there? They are not really for although they really add to the aesthetics quality, because they are nice, glossy and shinily painted. Okay, they have a nice glossy surface, very good painting, but they are actually added for the acoustics purpose. Okay, so they are added to enhance the acoustics inside this indoor office space. They act like a panel absorber and they try to absorb the irritating low frequency noise. In the same way, here also you can see these panels, they are sort of hanging from the ceilings and they are adding to the aesthetics quality also, but they are serving the purpose of enhancing the acoustics of this environment. Over here you can see some fixed acoustic panels in a hospital waiting area. So, you see it looks so beautiful, it looks like some architecture, installed these colorful tiles just to just for the purpose of enhancing the beauty of the structure, but enhancing the beauty or the aesthetics is a secondary, it is just an added advantage, but the primary purpose of installing these tiles is to provide firstly some kind of thermal insulation and also to provide some sound absorption and enhance the acoustics. So, they are usually installed to enhance the thermal insulation and to enhance the acoustics of the environment, and they can be beautifully painted, beautifully cut and lined along the walls. So, the aesthetics becomes just an added advantage to the actual primary functions of these particular fixed acoustic tiles. Here also you can see in the coffee shops, it seems like they are adding so much of aesthetics, but they actually serve the purpose of again absorbing the sound. So, what is the working principle behind this? In the panels you have got some sealed air cavity, it acts like a constrained acoustic medium. So, whenever you have got any kind of acoustic cavity, any kind of cavity with an acoustic medium such as an air, and it is confined on various places, So, at every rigid wall you have a condition that the sound pressure, okay, the velocity suddenly when it hits the rigid wall, the particles cannot go beyond the rigid wall. So, the velocity has to become 0 at the rigid walls. So, whenever you have got some kind of medium within confined rigid boundaries, it has to satisfy the condition that the sound waves, they will reach their velocity minimum at the boundaries, and in such confined medium what happens is that they can only allow the sound waves to be there at a certain frequencies, okay, because they have to satisfy that condition. So, let us say something like this to sort of explain this. This is the rigid wall and we have got some confined acoustic medium, So, here the particle velocity has to become 0 on all these walls. So, what kind of wave can you observe? You cannot have any random wave. Maybe you can have a wave like this, or you can have a wave like this. So, this shows the velocity profile. Okay, so this shows the acoustic velocity. It can reach a 0 value. So, one wave could be like this. Then you can have a wave like this. Then you can have a wave like this. And so on. So, always the condition this has to be satisfied that at the end points the V has to become 0. So, you cannot have any frequency you want, you can only have waves of a certain frequency, certain frequencies, only certain frequencies can exist within such confined acoustic medium that are surrounded by rigid walls, because at the walls the acoustic velocity has to be 0 at the rigid walls, okay. Acoustic velocity or particle velocity is becoming 0, and to satisfy that your velocity wave front, it has to reach a 0 value at the end points. So, the shape cannot be any arbitrary, I cannot have any arbitrary shape as I want, it has to reach a certain 0 at these points. So, only certain allowable frequencies can exist. So, with this understanding, what we come to know is that if suppose a panel has got a constrained sealed cavity, it can only allow certain frequencies to exist within it, which means that at certain frequencies only, if the sound is hitting, the panel will, the air cavity inside the panel is not going to get excited at all the frequencies. It will only get excited at certain frequencies which match with the allowable frequencies of its medium, which satisfy this particular condition here, and only at those frequencies whenever the sound wave is hitting, suddenly the acoustic medium is going to get excited, the sealed cavity will undergo large amount of pressure fluctuations and particle velocity fluctuations. So, whenever this happens, so those frequencies which are allowed within this constrained medium, they are also called as, these frequencies which are allowed, these are also called as the natural frequency, which means that only, or the modes, which means that these are those discrete frequency of sounds that can exist within this medium. Other sounds, they get automatically dimmed because they cannot exist within this confined medium. So, whenever your sound wave inside some room and with acoustic panel installed in the room, then the incident frequency of the sound wave matches with one of these natural frequencies of the panel, then the phenomenon known as resonance occurs. What happens in resonance? So, whenever this happens, so in that, so because panel absorber is the first kind of resonance based absorber, so the phenomenon of resonance needs to be understood. What it means is that we have got some kind of an acoustical medium where only certain, certain sounds with only certain discrete frequencies can exist. So, whenever your incident frequency is matching with that allowable discrete frequency or the natural frequency, then suddenly the medium is going to get excited at a very high level. There would be an acoustic coupling or a resonance, which means that suddenly you will have the sounds with very high amplitude or vibrations with very high amplitude, whatever is getting excited. So, very high level of excitation will happen in this case because it is hitting the panel and the cavity inside is getting excited. So, the panel itself will start vibrating largely. So, the panel is going to vibrate at a high amplitude at this particular resonance, and now whatever the sound wave is being incident, it is somehow using up all its energy to drive the panels. Okay? So, the panel is a stiff panel with a certain mass. Suppose you have to sort of vibrate the panel, okay? You have to fluctuate the panel. So, initially the panel, it was at rest, but then due to the incident sound wave hitting that panel, the panel is now getting excited. So, initially it was at rest and now it starts vibrating heavily. So, to vibrate itself, the acoustic energy or the sound energy is getting used up. Okay? It is doing work against the panel mass in order to vibrate it, and this causes the dissipation of the sound energy. So, what you can say here is that in a very crude way you can say that suppose I am in a room, there is some kind of noise source and there are these acoustic panels installed. So, whatever my sound wave I am creating or whatever the noise source is, whenever the frequency of the noise source matches with the natural frequency of that panel, then that frequency can create resonance, which means that it can help acoustically couple with the panel. Or maybe another way of saying that frequency, when the noise source is creating a frequency which matches with the frequency of the panel, then at that frequency whatever sound waves are coming out of the noise source, they will actually get used up in driving the panels to vibrate at high amplitudes. So, the noise is going to go down, but the panels will be set into vibration. So, basically the energy going into the room is now getting sort of absorbed into the panel and is used and is going into that confined space of the panel to vibrate those panels. And the dissipation happens because the work is being done to vibrate them. It also happens because whatever vibrations are created, they create shear deformations because of the vibrations. That also uses up a lot of sound energy. Now, so that the natural frequency of the panel, that becomes very important because it is at that frequency it behaves as an absorber. Okay? It can absorb the sounds at its natural frequency. So, what is it? For a fixed medium with a concealed cavity, the natural frequency is given by this formulation here. So, which means that Lx is one dimension of the panel, Ly is the other dimension of the panel, and you know that a set of discrete frequencies can exist. So, the natural frequencies, they can be a set of discrete values. So, and H is the thickness of the panel or the thickness of the concealed air cavity within it. Okay, this one. So, what it means is that, let us say for example, if H was equal to 1 and the speed of the sound in the panel medium was somewhere, let us say 500 or 1500 like that, and your Lx was, let us say 2, Ly was also 2, then what it would mean is that the very first natural frequency or F naught would come at this particular value. L would be, if L is 0, M is 0, then the value becomes 0. You do not want a 0 value, so you will start with L as 0 and M as 1 like that. So, let us say I make 1 as 0 and 1 as 1. So, this is 1 by 2 plus this is 0. So, this will be your first frequency where L is 1 and M is 0. Then if you, the next frequency you can get by putting L as 0 and M as 1, and in this case it would be the same value because both Lx and Ly are same. Okay, and then you will have the mode where L is 1 and M is 1, and you will get yet another frequency. okay, a different frequency, and then you can have another mood where L is equal to 1 and M is equal to 2, L is equal to 2 and M is equal to 1, and so on. They can take these discrete values, and for each value you will get a certain, for each of these integral values of L and M you will get a certain frequency value. So, a lot of discrete frequencies are there, and these become the set of natural frequencies of the panel. So, whenever the incident sound wave has a frequency same as one of these values, okay, one of these values that you are obtaining, then it will act as an absorber. So, obviously the absorption characteristics would have a peak like this, where each will correspond to a certain mode of the panel. Okay. So, this is how the typical absorption characteristics with respect to frequency should look like, okay, for the panel, because it has a set of discrete natural frequencies corresponding to an L and M mode. In the same way, for a freely suspended panel we have similar kind, just it is twice of whatever value you obtain for a fixed one, and once again you can put L is equal to 0, M is equal to 1, M is equal to 0, L is equal to 1, and slowly putting these different integers you can get the different set of discrete frequencies which are the natural frequencies of the panel. And if the incident frequency is any of these natural frequencies, then the panel will act as an absorber. So, once again its absorption characteristic should have multiple peaks corresponding to whatever its natural frequencies are. Okay. So, F0, F1. So, we will get a set of different frequencies for the different L and M values, and corresponding to that we will get a multi-peak sound absorption curve. Okay, so what is the effect of this concealed air cavity? So, here we know that a lot of energy is getting dissipated to vibrate the panel. So, some work is being done against the panel mass or inertia, and also due to the shear deformations which are caused when the transverse waves are being generated in the panel. But in addition to that, we have a concealed gas. Then suppose we just had a hanging panel, these two mechanisms would operate and dissipate the sound. Okay. So, in case of freely hanging panels which do not have a concealed cavity within them, these two mechanisms take place. But just in case we have a concealed cavity, then there is additional absorption due to the resistance faced by this concealed cavity or the concealed air resistance. Because here when the panel is vibrating, it is trying to, when it vibrates like this, it tries to compress and expand the concealed air cavity, and this leads to irreversible gas heating and the loss of sound energy. So, there is an additional mechanism that comes into play because of the concealed air cavity. Suppose instead of concealed air cavity, now you had the porous fillings. So, what would happen? Again some energy is used up because of the panel vibration. So, the first two mechanisms for dissipation of the sound is definitely the same, and then if there was a concealed air cavity, there would be a concealed air resistance as well. Suppose it is an absorber lining, and now that you have a porous material, the absorption, there would be an additional mechanism which would be the absorption by the porous material. It would enhance its absorption at the higher frequencies or the panel modal frequencies. So, let us see and see experimentally what we have found. So, effect of porous absorber lining. Suppose you have got some panel and inside it this is your panel, and then it is backed by a rigid concealed air cavity, rigid filled with porous absorber blanket. So, when there is no absorber filling, this is the sound absorption coefficient, but with the absorber filling, what is happening is that now the absorber is helping both in the low and the high frequency zones. So, it does not matter whether it is low frequency or high frequency, it will help both ways. Why? If you introduce absorber, it adds additional damping. Okay. So, the frequency, so typically the absorption values get enhanced because you know that at resonance particle velocity are the maximum as they are flowing through into these absorbers, and hence higher level of absorption is taking place at the resonance. So, wherever you are getting the peak essentially, so without the absorber lining, whatever are the peaks that you were getting, if you add the absorption, you will get the same peaks, because at that peaks your acoustic particle velocity is the maximum. You are having the maximum vibrations and the maximum fluctuations, and hence this highly vibrating, this large amount of acoustic velocity with which particle which are vibrating, they will enter into the absorber filling. So, they will enter at a higher velocity into the porous material, and the viscous losses would increase because of the increased particle velocity. So, even at lower frequency you are getting a peak, and then you have introduced an absorber filling, then the thermoviscous losses will also rise at those high particle velocity regions, and the peaks will get enhanced even at low frequencies, okay, like this. So, the peaks get enhanced. Now, what is the effect of air cavity depth? So, again I was saying that suppose most of the times these panels are used in the closed indoor spaces having rigid walls. So, in the closed indoor spaces with the rigid walls, again the condition has to be that the particle velocity has to reach 0 at all these rigid walls. So, only certain level of wave fronts can exist, as you can see here, and so on, because the velocity has to be 0 at both the ends. So, this is suppose the opposite walls of some room. So, only certain allowable frequencies can exist within this room. Now, you see here that the velocity is maximum at lambda by 4 away from the rigid wall. So, if the wave front is something like this, at lambda by 4 you have got the maximum velocity away from the rigid wall. Even if the wave front is like this, again the nearest distance from the rigid wall where we are getting the maximum acoustic velocity is lambda by 4. Even if we have this kind of a mode or the wave front, the nearest distance from the rigid wall where we get the maximum acoustic velocity is lambda by 4. So, at lambda the maximum particle velocity will occur always at a distance of lambda by 4 away from the rigid wall boundary condition. Hence, let us say with this knowledge we have got some confined room, and let us say we are hanging the panels, okay, in that room. So, what if we keep the length as lambda by 4 for these cables? What will happen? Then the panel, then we know that the particle velocity reaches a maximum at lambda by 4, okay. So, if the panels are kept at a distance of lambda by 4 from the rigid wall of the room, then the particle whatever the waves are generated in the room, they hit the panel with the maximum velocity here. So, basically the sound waves will be incident on the panel at the highest velocity, and due to which the losses will be higher. So, if the lambda by 4 distance is maintained for a panel, between a panel and the room wall or the room boundary. So, if you maintain a distance of lambda by 4 between the panel and the boundary of the room, then the absorption enhances and reaches maximum, enhances and reaches the maximum value. Why? Because at this point the sound waves will hit the panel with the maximum acoustic velocity, and whatever phenomenon we were absorbing, it will get further enhanced, because the higher velocity with which they hit the panel, the more energy gets used up in vibrating the panel, and the more energy gets used up in going into the absorber filling and getting dissipated as heat, okay. So, if you maintain the panel, so whatever, suppose you are having a hanging panel or you just have a fixed panel and you are thinking where should I install it to get maximum benefit. Whatever is your frequency of interest, suppose you want to curve down a frequency of 1000 Hz, then you would first find out what is the lambda corresponding to that 1000 Hz. So, it would be 343 by 1000. So, the value of the lambda that you get, you do lambda by 4, that would be the best distance to keep your panel away from the rigid boundary of your room, because at that place the absorption by the panel would be the most effective. So, this would be the distance at which panel will work the best. Okay, so some advantages of these panel sound absorbers, they are obviously non-perforated and non-fibrous. So, all the limitations of the porous fibrous absorbers are now getting solved. So, they are more durable, they do not have that high maintenance requirement. So, even with low cleaning and maintenance, they work because they do not have any exposed pores or holes and no such loosely bonded fibers, okay. No loosely bonded fibers that can fall off, it is a stiff lamina. So, that kind of maintenance is not required, no need for these maintenance. So, low maintenance and cleaning requirement compared to porous fibrous absorbers, and more durable because they do not get clogged up due to the continuous usage. And then the surface can now be painted and treated without affecting its acoustic properties, and hence they can be used for as the aesthetic elements, and they are effective for targeted low frequency absorption. So, basically whatever limitations you had with the porous fibrous absorber, the porous fibrous, the limitations was that low frequency absorption is quite poor, okay. At the low frequency they are not able to absorb properly. You cannot do surface treatments on them because then the pores can get blocked up and the absorption can go down. With the continued usage, the air contaminants and the dust particles in the air can again block up the pores and the fibers, and they can still make the absorption go down. So, they were not durable also, and lot of cleaning and maintenance was required. So, all of these limitations are now avoided by using a panel sound absorber. What are the limitations? Now, although they can give you targeted low frequency absorption, I mean targeted means that only at certain range. So, typically the absorption peaks, they are very sharp in nature, okay. For a porous material, let us say this is your absorption, it looks like this, very broad band after a certain frequency range, poor at low frequencies. But for a panel absorber, SSE looks like this, sharp peak at low frequency. So, which means that broad range absorption again becomes tricky and difficult. For that you need to have numerous such panels with different geometries, each of them giving a peak at a continuous different frequency and combining them together, which again is not practically feasible. So, broad range absorption is very difficult. Then they have much higher weight compared to the porous fibrous treatments, because essentially porous fibrous, they have lot of air spaces and voids, and their velocity and their density is very low, they are very low weight, low cost solutions. But panels, they are stiff lamina, they are higher weight and higher density. Their usage and installation is also limited only to some indoor spaces. They cannot be installed just anywhere in compact machineries because of the shape that they have to maintain, the air cavity depth that they have to maintain, and their mounting conditions. So, because of their construction and their design itself, they cannot be used in machineries with complex contours, whereas absorbers just can be lined anywhere in the machinery. Some applications, the panel absorbers, they are the most common bass absorbers, effective in reducing most of the echoes, and specially used in the indoor spaces like small rooms, houses, office cubicles and restaurants, where you can find them in the form of suspended ceilings, hung false ceilings. So, whatever false ceilings are there, suspended ceiling panels are there in these office cubicle spaces, restaurants and various other buildings. They are panel absorbers. Then the gypsum board partitions and the wood partitions inside the houses, they also serve as panels. The wooden floors, the acoustic tiles, the panel walls, then the bass absorbers in the speakers and the musical instruments, they are all panel sound absorbers. So, some pictures. This is a gypsum board partition at home which is acting as a panel absorber and also adding to the aesthetic value and creating a partition between two living space. Here you have got these wonderful acoustic tiles acting as absorbers. You have these hung freely suspended acoustic panels on these in this office cubicle. Then you have got again these various kind of wooden tiles on the floor which act as panel absorbers and so on. So, thank you for listening.